Swayam Prabha. Digital India. Educated India.
Okay, I think we will get started. Since we just started about register allocation, hopefully there are not too many questions on this, but after I finish with usage-based register counting, I'll take a few more questions before we move forward. Again, we are not seeing all of these things in the same order in which you would normally see it in a compiler design course. So I'm trying to build up this required background for this in terms of what kind of instructions you will see, what does it mean to say a live variable, what is the live range, and so on and so forth. So intuitively, the idea is that if the value has to be preserved, then we say that at that point in program, the value is live. And if two variables are live at the same time, then they conflict with each other, and therefore they have to be given different registers. That's essentially the point that we are trying to make. There are some finer level details which we have understood by going through some of these examples. Again, as I mentioned, once Professor Ketkar completes his lectures on data flow analysis, you would completely understand what is live variable, how live variable analysis is done, and using live variable analysis, how we will actually do diffuse chains and so on and so forth, which is what is really required for writing a register allocator. Okay, let's try to deal with these things more in an intuitive way. And as I mentioned earlier, two variables conflict with each other if they are live at the same point. But a more precise definition is to say that if one variable is live at the definition point of the other, right? That's it's the same thing with some finer level details. Let's not get into this right now. Okay, so in this particular thing, if you see, variable S2 is live when, variable S1 is live when S2 is being defined. Therefore, S1 and S2 conflict with each other. Similarly, variable S3 is live when S3 is being defined, and therefore S2 and S3 conflict with each other, and so on and so forth, right? Whereas if you look at S1 and S4, neither S1 is live when S4 is being defined, nor S4 is live when S1 is being defined. Therefore, S1 and S4 do not conflict with each other, and possibly they can share the same register. Whereas S1, S2 or S1, whereas S1, S2 or S2, S3, if you look at it, they conflict with each other. So is S3, S4, right? Okay, so as I mentioned earlier, how do you compute this live range? You basically compute what are called the diffuse chains, and then from there you compute the live range. Okay. Before we go into the register allocation, let's just try to look at in the different passes in the compiler, where exactly is register allocation done, right? It is done on the target machine code, okay? So typically it is done after the code generation phase, because code generation phase assumes infinitely many registers, or what are called temporary registers, right? Or logical registers, or whatever they are called, and the code is generated. So this is done after that, okay? And to a certain extent, it is done after you have done certain machine dependent optimizations as well. But as is always the case, many of these compiler passes have to be run repeatedly. So even after you do, and see, for example, you do machine code generation, you do machine dependent optimizations, you do register allocation, you do instruction scheduling, and maybe there is something else that needs to be done. So you will try to do one more level of local register allocation. And then after that, you will go and then possibly do one more level of machine dependent optimization and so on, because many of these passes are done many times iteratively, right? But roughly, register allocation is done after code generation, after the machine dependent optimizations. Okay, it could be done either before instruction scheduling or after instruction scheduling, right? Again, as I'm going to talk about it a little later, that register allocation and instruction scheduling kind of interfere with each other, and people have talked about what are called pre-pass scheduling, in which instruction scheduling is done first and then register allocation is done later. or post-pass scheduling, in which register allocation is done first and instruction scheduling is done later. There are also what are called hybrid allocation, in which you try to do instruction scheduling and register allocation in some sense together. Okay, so if you look at the LLVM compiler, right, LLVM compiler does register allocation after it has done the SSA, the static single assignment form reduction, means reducing the program into the static single assignment form, and then after doing certain optimizations on the static single assignment. In fact, LLVM does register allocation on the static single assignment, which is slightly different. So I will not be able to get into that, but you can see that it happens after you do many of these machine independent optimizations and then reducing it into the static single assignment form. And in the static single assignment form, it basically does register allocation. So looking at GCC, then GCC does this in the backend. Okay, it is done after instruction scheduling and after register class definement and so on and so forth. Again, these are the sequences of steps or passes that are done by the GCC compiler. Sorry. Okay, now let's move on to one simple register allocation, which is basically using usage counts, right? As I mentioned earlier, the goal of the register allocation is to assign registers to variables. And then we want to choose those variables which are more often used in your program, because if you assign registers to them, to the most frequently used variables, then their accesses can become faster and therefore your program execution would become faster. So you essentially want to allocate registers to variables which are accessed more frequently. That is what is profitable, right? And that is essentially based on how often they are being used, or what is called the usage count, right? And of course, when you do this register allocation, as I mentioned earlier, if two variables do not conflict with each other, right, then the same register can be allocated to them. That is, the same register can be allocated to multiple variables as long as they don't conflict with each other. So the register usage-based register allocation method essentially looks at the program, in some sense try to compute, right, which variables are being used more often, and then tries to allocate registers for that. Okay, so let's take a very simple program in which I have a while loop, and inside that while loop I am accessing variables like sum and I and so on, right? And of course there are a few statements outside of the while loop, right? And variables like C is used only outside the while loop and not inside the while loop. Let's look at the control flow graph for this, and in this particular case the control flow graph has instructions which seem to be using all the program variables themselves. This may not necessarily be the case always, because they may break this down in terms of multiple instructions, and there could be temporaries that are introduced by the compiler and so on. But in this case, things are very simple. These are the program variables. And of course, if you do some level of machine code generation, then some of these program variables or variables would also be changed into temporary registers, etc. But let's leave that for the time being, right? So this is the control flow graph. Again, you can see that the while loop condition is being checked here. If the condition is satisfied, then you go through this path and then repeat the while loop. If the condition is not satisfied, you go out here, and then of course the condition has been reversed here. That is why you see the true and false on the other side. Okay, the while loop condition is I less than or equal to 0, whereas here we are checking I greater than 0. That's the only difference. Okay, so this is what is happening here, right? If you take this graph and then try to identify the usages of these variables, you can see that variables sum and I are being used more often than variables like C. More specifically, if you look at the variable I, it is being accessed once here, twice here, right? So it is being accessed within the loop 2 times, and it is actually fetched or read twice and written once. So basically there are 3 accesses to variable I within each loop. So if this loop iterates 100 times, then there will be 300 accesses, right, made to variable I. Similarly, if you look at the variable sum, it is being read once and written once within each iteration. So the variable sum is going to be used 200 times inside the loop. And other than that, there are a few other usages that you can count from here, right? And now if you compare this with the usage for, let us say, a variable like C or square, right? They are being used once or twice outside of the loop, right? For example, square is defined once and read once, right? And C is defined here and read once, and so on. So essentially what we do is that you count this number of times each of these variables is being defined and used, and then you take the total value, right? And then based on this, you can decide that variable sum and I have to be allocated registers. So if you have only two registers, then variable sum and I can be allocated those two registers because they are often more frequently than variables like C and square. But of course, you can see that after the while loop is over, I is no longer needed. Therefore, the register that you have allocated for I can also be used for some other variable, which is in this particular case maybe square. All right. So if you look at this, that's really what is happening here. We use the same register for variable I and square, since there is no point in program where both of these variables are simultaneously live. So if you do that, essentially this is what you get. You allocate register 2 to sum, register 3 to I, and then square also shares the same register. I'm assuming register 1 is not being used here. Assuming two registers, register 2 and register 3, and I have allocated those two registers to sum and I, and I'm also sharing it with square. Variable C will reside in memory, and it has not been allocated a register, because in this particular architecture or for this particular register allocation, we have assumed that there are only two registers. Okay, so one last slide on usage based this one. So question is, what happens if I don't know how often the loop is going to be executed, or how many times the loop is going to be executed? Because in programs, you could actually determine the number of times it goes through the loop can be determined at runtime, or there could be control flow paths within the loop, and therefore I can't exactly calculate how often something is going to be executed, right? The simple usage-based register count mechanism essentially makes certain simple assumptions. For example, whenever there is a loop, it assumes that the loop is going to be executed. If the number of times it's going to iterate is not known, it will assume that it is going to execute 10 times or 100 times, right? If there is a control flow path, and if it doesn't know how often the else part will be taken and how often the true part would be taken, it will simply assume that either they are equal, or maybe it will assume, depending on the type of condition or the type of branch that it is making, that it's going to make 75, 25, whatever it is. And then based on that, it's going to do register allocation. Obviously, that kind of a register allocation would work better if those assumptions hold when the program runs. If the assumptions do not hold, or maybe the assumptions are other way around, for example, if you have assumed that the then branch is going to be taken 75% of the time and the else branch is going to be taken 25% of the time, you would have counted certain usage statistics. That usage statistics may be wrong if it is the other way around. For example, if the then branch is taken very few times and the else branch is taken most of the times, then obviously your usage counts would have been wrong. And in those cases, the register allocation that you would have done may not necessarily be very beneficial. Nonetheless, you will end up generating the right kind of a code, and the code would still execute correctly, maybe not very efficiently. Again, you could take some of these statistics using some kind of a profile-driven approach also, where you run the program for some sample inputs and then gather some of these things. So there are many ways of doing it. The simple usage-based count mechanism essentially assumes, right, these simple things and then moves forward. Even when you talk about this graph coloring based register allocation and other cases, when you have to decide which variable to spill, you will again go back and ask the question, which of these variables you use more often and which of these variables is used less often. So in some sense, you need this count, and this is a rough estimate of what is going to be useful. Okay. The second thing is what happens if you have nested loops. So if you have a nested loop, then of course, the variables inside the body of L2 is more often going to be used than the variables which are used outside of the body of L2. It's also possible to do register allocation for some variables which are within the body of L2, but then they may not be allocated the register outside of that loop, or vice versa. Some variables could be, some variables in the outside loop can be allocated registers, whereas they may not be used inside L2, and therefore those registers can be reclaimed and used for some other things. So again, there are some simple rules that you can follow. Right, for example, if a variable is allocated a register outside of L2, right, then what happens is that before you enter L2, you actually save it into memory and then free the register. And then again, after you exit this L2 loop and before you start executing the outer loop, you load it from the memory into that register and use it. Vice versa. For example, if a register is used only within that loop, then you use it here and then you spill it at the end and then release the registers and so on. So there are some simple rules. You can go through that to understand them, not spend time on that. So that's really how the simple usage count based register allocation works. Quickly estimates, right? Quickly estimates how often each variable is going to be used, which variables conflict with each other, and then based on that going to decide which variable should be allocated the registers. Okay, that's a very good question. So you're talking about the variable I here, which is being redefined as I is equal to I plus 1, correct?
Yeah.
And not only that it is being redefined within this loop, also outside of the loop it is assigned once, correct? Okay, now, okay, so what we are going to deal with this is that for scalar variables, right? Because eventually when you generate your intermediate code representation or the target code, all the variables are going to be scalar, and you are only going to have either temporaries or program variables which are scalars, right? Irrespective of the number of times it gets defined, you will assume that it is the same variable, right? And it's known by the same name. It is I here, it is I here also. So you are going to talk about whether to allocate a register to I or not. This is the simplest way by which you will deal with it. Okay. You could still ask the question, should I allocate a register for I over here, or should I allocate a register for I only over here? That's a slightly different question. We will come to it a little later on, right? But there are these multiple definitions, right? And this multiple definitions causes certain other complications, but leave that for the time being. So there are of course intermediate representations which avoid this static multiple definitions. By static multiple definitions, what I mean here is that I is defined once here. Let me just take the pen. I is defined once here, right? And I is defined again here, right? These are static. Statically, there are two assignments to I, right? There is an intermediate representation which is what is called the static single assignment representation, where such things are not allowed. One of these I's is going to be changed to I1, the other one is going to be changed to I2, and so on and so forth, right? And when you do that, of course, there are a few other things that you need to do to make sure that that representation is kind of consistent. But that representation, once you make it, right, it actually gives you a very nice structure, and certain problems in compilers can be solved in a much more efficient way under the static single assignment form. I think Subhajit, Professor Subhajit is going to talk about static single assignment, right? Okay, I'm sure that you have a lecture on static single assignment at a later point in time. In fact, the LLVM compiler uses the static single assignment. And when you have a static single assignment, then what it means is that different versions of the variables like I1, I2, I3 now can be treated as different variables, and they can be possibly assigned different registers. Okay, but for the time being, in all our discussions, we are going to assume that these variables, we are not going to assume a static single assignment form. We are going to assume that these variables are the same variables, and therefore they have to be allocated the same register if they are allocated a register. Later on, we will also talk about what is called the live range splitting, right? And when that happens, you will also talk about how to take the same variable, split it into multiple live ranges, and possibly assign either the same register or different registers for the different split values. Okay. So for now, we will consider this as one variable and think of allocating one register to it. So did I answer your question?
Yes, sir. Yes.
Okay. Any other question? Okay, let's move on, and hopefully at the end of it, we will again spend some more time for Q&A. So the question that we want to do now is that if I want to do global register allocation, that means that I want to consider the variables in my program, maybe at the level of a function or at the level of a region which is beyond basic block, and want to do register allocation for that. What are the mechanisms by which we can do that? Okay. The essential problem in global register allocation is that if two variables conflict with each other, that means that they are live at some point in program together, then they have to be allocated different registers. So this information of whether two variables conflict with each other or not can be captured in the form of an interference graph, where the nodes of the graph essentially represent, right, the variables in the program or the values in the program, the variables in the program or temporaries in the program, right? And an edge between, right, two nodes essentially means that those two variables conflict with each other, right? So this is essentially what we call as an interference graph. So you have all your variables in your program, you have calculated their live ranges, and you have also calculated the information about which variables interfere with each other or which variable conflict with which other variables. Now this entire information can be represented in the form of an interference graph, right? Where the nodes of the graph are nothing but the variables in your program. Variables meaning program variables as well as temporary variables or temporary registers, whatever you want to call them, right? And the edges between the variables or edges between the nodes essentially represent the fact that they conflict with each other. Okay, the live ranges of V1 and V2 overlap. Now, the problem that we want to do is that now you have a graph consisting of n nodes and some number of edges. You want to color this graph in such a way that two nodes which are adjacent to each other, that means that they have an edge to each other, do not have the same color, right? So you have a graph in which there are some number of edges. You want to color the nodes of the graph using different colors such that two nodes which are adjacent to each other, that means that they have an edge between them, do not have the same color, right? And you want to color it using minimum number of colors, or you want to color it within a given number of colors, and so on and so forth. That's essentially what is called the graph coloring problem. Graph coloring problem has been studied in graph theory extensively. Now what we have done is that we have mapped the register allocation problem to the graph coloring problem, and therefore we could use any of the solutions that the graph coloring problem has, any of the heuristic solutions that the graph coloring problem has, and we can apply that in order for us to do register allocation, right? So again, some background here. A graph is said to be k colorable if each node can be assigned one of the k colors such that no two nodes which are adjacent to each other have the same color. This is the same problem that we have defined. Okay. I think that is essentially restating the same thing, right? The k coloring of the interference graph can be directly mapped to the legal register allocation problem, because what we are trying to do here is that we want to give registers for each of these variables, and we want to give different registers for variables which conflict with each other, and variables which do not conflict with each other can potentially have the same registers. Okay. the problem of whether a graph is k-colorable or not is NP-hard for k greater than or equal to 3. Therefore, people suggest using heuristics to find approximate things. Okay, so this is one problem that we have. The other question is that supposing, let's say, somehow I find out that this particular graph is not k-colorable, where k is the number of registers that we have. Then what should we do? Right? So I have an interference graph. I know that that interference graph cannot be colored using 4 colors, where 4 is the number of registers that I have. Then what should I do? The answer is easy. Pick one of the nodes or pick one or more of the nodes, right? And then keep them in memory and only color the remaining, and then see whether the remaining nodes can be colored using 4 colors or k colors, right? So if it is not k colorable, right, repeatedly select less profitable variables and then keep spilling them, right? And when you spill them, what does it mean to say spill them? It essentially means that those variables are going to reside in memory. The remaining variables are the ones which would be colored, which would be given registers, right? So you have to spill as few variables as possible so that the remaining graph becomes k-colorable. So essentially what you do is that you look at the graph and then see whether it is k-colorable. If it is not, pick one of the nodes, right, which is less profitable, spill that, and then see whether the remaining graph can now be colored using k colors. If that is not the case, again you iterate through this process until you get a k-colorable graph. And that k-colorable graph is now colored using k colors, and the variables which are identified as spill variables they reside in memory. That's essentially how one could go about using the graph coloring problem for register allocation. But this method is somewhat inefficient in the sense that a priori you decide and then spill some nodes, and that may or may not be necessary. So Chaitan came up with a clever algorithm for doing this. That's what we are going to talk about next. Okay, but before we go into that, let's just see an example of live ranges and then this interference graph and so on. I'm going to use this example here, and you can see here this example has 4 basic blocks, right? Each one of the basic blocks is in different color font, right? The first basic block has a sequence of about 6 instructions. Then you have a then block and an else block. Each one has 1 instruction each. And of course, after that, you have a merge block, right, which also has 1 instruction. Here we have many of these temporaries, S1, S2, S3, and so on and so forth. Right? Now, let's look at the live range of these variables. Again, you have to calculate the live range by finding out whether the variable is live at different points in programs. And then, of course, after you have calculated the live range, you also have to figure out whether they interfere with each other or not. So we have seen how to do that. And of course, you're going to see more about how to compute liveness information, how to compute diffuse chains, etc. in a subsequent lecture. So I will skip the details. And then I will simply say here for the different variables that we have, S1, S2, S3, S4, S5, these are the live ranges. Okay, these are the live ranges. At a later point in time, you can go back and verify whether this is indeed correct or not, right? But I presume this would be. Okay, now given these live ranges, let's ask the question, what is the interference graph? The interference graph is what is shown on the right-hand side. For example, if you take variable S2, you can see that S2 interferes with S1 because S1 is live when S2 was defined. Similarly, if you look at variable S3, right, S2 was live when S3 is defined, and therefore S2 and S3 interfere. So are the cases for S2 and S4, S2 and S5, and S2 and S6. So if you look at variable S2, it interferes with every one, and therefore there are edges from S2 to every other node in the graph, right? Whereas if you look at variable S1 and S5, they do not interfere with each other. Therefore, there is no edge between S1 and S5. If you look at variable S5 and S6, they interfere with each other, therefore there is an edge. S6 also interferes with S2, which we saw earlier, but those are the only two nodes with which S6 interferes. All right, so given the control flow graph, given the variables and their live ranges, we are now able to reduce this into what is called an interference graph. Now, by looking at the interference graph, we can now say whether this interference graph can be colored using some number of colors or not. For example, let us say that we want to do register allocation in a machine which has only 4 colors, 4 registers, right? The question is this graph 4 colorable, right? Because this graph is small, we can even try this manually, and then we can see that if I keep giving these different colors, I should be able to do it, right? Note that S1, S2, S3, S4, right? They all have different colors because they are adjacent to each other, right? You can see that there is a click between S1, S2, S3, S4, right? Each one of them is adjacent to every other of these 3 other nodes. And therefore, they are given 4 different colors. S5 is given green because S5 is not adjacent to S1, which is given the green color. S6 is given blue because it's not adjacent to S3. S6 could have been given red or yellow, right? And similarly, S5 could have been given blue. But if S5 is given blue, S6 cannot be given blue. That is also there. Okay. Right? So this is essentially what we are going to call as the graph coloring problem. Now let's ask the question, is this graph 3 colorable? Right? Can we color this using only 3 registers? The answer is no, because you can color S1, S2, S3, but then S4 cannot be colored because all the 3 colors, green, red, and blue, are already taken and then those nodes are adjacent to S4. Therefore, this cannot be colored using 4 colors. So in this particular example, if you want to do register allocation for this control flow graph using 3 colors, then you have to decide to spill one of the nodes, right? You could have spilled any one of the nodes, but if you have spilled S6 or S5, it still wouldn't help, because even if you spill S5 or S6, S4 could not be colored because S4 is adjacent to S1, S2, and S3, right? Therefore, it cannot be given the same color as any one of them. And of course, all 3 of them require different colors because they are all adjacent to each other. So in this case, necessarily, you must spill one of these 4 nodes, whichever one which is less frequently used, and you would try to spill that, right? And of course, once you spill that node, the other nodes can be colored using 3 colors. Right. How do we identify which node to spill? Of course, you have to use this notion of least usage, but then to figure out that one of the nodes S1, S2, S3, S4 only needs to be spilled. Because if you have taken, let's say, S6 is the least use, it has only 1 use here. If I spill S6, is it useful? The answer is no, right? Because if S6 is spilled, you still wouldn't be able to color S4. So is the case for S5. So to figure out that you have to spill one of these nodes, right, is also an important thing. So let's see how we are going to do this and how we are going to do this using Chaitin's algorithm, right?